Hey guys, Tanner here. I'm sitting outside of Cerca right now, 2014, about to go check it out. I'm really excited. I went last year and there's a lot of cool projects, so hopefully we can snag an interview or so. Yeah, let's go check it out. Alright, we're kind of walking around the posters now. Not a lot of people here right now because it's in the morning, but as you can see, you got all the posters behind them. There's hundreds and hundreds of projects. This is awesome. This is kind of what you can expect. It's going to be projects upon projects. There'll be hundreds of people here later. Right now I'm over in my homeland, the chemistry area. Got quite a few projects going on. I think there's almost 20 of them. Hopefully the person on this poster will come later. We can get an interview. Looks pretty interesting. Found Carlos's poster. This looks pretty interesting. Good work. Alright guys, spent about half an hour walking around looking at different projects, kind of getting some information so I can come back later and hopefully get an interview. See you then. Alright, we're back for round two. Let's get some questions answered. As you can see, it's a much different scene than this morning. We just caught the group that we were looking for before our main presentation. Let's join in.
So then we thought, okay, maybe we can tune these colors. So let's put in some spacers. So we added in a bifold spacer versus a monofold spacer. And we synthesized those and we saw the exact same thing. We could change the color and that was really cool. And they were fluorescent as well. Right. So that's another good point. And then that way we'll do it. 1, 2, 1, 2, 3. Okay? So, those are your spacers. The R group out here. Oh, okay. So these are the spacers. All the spacers are the bipounds, but we have a different R group because each one of these R groups is going to...
Some really cool research. Good job.
We are looking at two dynamic Riccati equations over timescales, and a timescale is a closed subset of the real numbers. So two good examples of a timescale are the real numbers and the integers. We can jump forward and backward in between points of these timescales using the forward jump operators sigma and rho. Sigma just jumps you to the next point in the timescale, rho jumps you to the previous point. So in the integers, sigma applied to 1 would give you 2, and rho applied to 1 would give you 0. And the spacing between points, sigma of t minus t, is equal to the graininess function given by mu. And in the timescales that we're looking over, mu is a constant. So we're looking at a timescale basically like the integers, except that the spacing between points is different. You can also define a derivative over timescales, which is given here. Basically how that derivative works is that you look at the next point, how high it is, the previous point, how high it is, and look at the spacing in between the two and divide the two. And that gives you basically your derivative. So we're looking at these two dynamic Riccati equations, one up here, two down here. This first dynamic Riccati equation comes from using this substitution in the second order dynamic equation shown here. This second order dynamic equation here, we have used to develop the second Riccati equation using the same substitution. So we've looked at these two dynamic Riccati equations over the timescale μz, which is, as I told you before, like the integers, but there's different spacings between points. And we've looked at timescales with different spacings in between points. And so here are what solutions look like for the first Riccati equation and the second Riccati equation over various spacings between points mu. The red line shown here shows you what the solution behavior of the first Riccati equation is over the real numbers. Basically when spacing between points is arbitrarily small. Line shown here in blue is the solution where we've changed the spacing in our domain just a little bit by 0.2. And you can see that even though we've introduced spacing in between points, the solutions, at least over this domain interval that the real numbers, this equation is, it lives over, closely approximates it. Basically when spacing between points is arbitrarily small. Line shown here in blue is the solution where we've changed the spacing in our domain just a little bit by 0.2. And you can see that even though we've introduced spacing in between points, the solutions, at least over this domain interval that the real numbers, this equation is, it lives over, closely approximates it. As we increase the spacing between points, you can see that an oscillatory behavior kind of develops, where solutions jump down, then they jump back up, and they jump down a few more times, and they jump back up. And I'm going to talk about this later, but we're trying to describe that oscillatory behavior using a band structure. One thing that we...
Thanks, Max. That was awesome. Great work. All right, we're here with another project. Let's find out what it's about.
Alright, we did the impact of ethnic diversity in the workplace in Marshfield and Eau Claire, Wisconsin. We looked at 3 different categories of companies: manufacturing, hospitals, and restaurants. Some of our results are kind of interesting. We saw that a lot of the Hispanic workers that stayed in the same restaurant, the same industry, had a completely opposite view of what their company was like than the Caucasian workers in that place. And that was kind of an interesting result, because in the same company you can have a very different spectrum of answers based on the ethnicity of the individual. We found that the hospital was do that regardless of ethnicity, and that manufacturing tended to be more primarily dominated by Caucasians. That people was just lacking. So when we talked to HR, we was lack of
All right, we're just leaving Cerca now. Another great year. Awesome turnout, awesome projects. Glad I could share that with you guys. See you later.